Hello, AP chemistry students. Sorry I can't be there today. The flu turned into a fever, so I got to stay home today. But I didn't want you to fall behind, and I promised that I was going to teach you about Beer's Law, so here's a video to help you get through that. We're going to try to review quickly some solubility problems that we didn't get to yesterday. I'm going to try to get through Beer's Law. A little reminder about your AP classroom assignment. You will probably want to have a whiteboard so you can jot down some notes as we go. I'm going to take my ugly mug off of here and then get moving on the notes. All right, so when we talk about solubility, there's one term that sometimes comes up. It's called sparingly soluble. So, Honor, would you read this slide for us? Thank you, Honor. And as you can see from the chart, there are these solubility terms that we looked at yesterday, but I wanted you to see also this iodine chemical compound. Iodine being bonded to itself is purely nonpolar. Over here we've got, in this chart that we looked at yesterday, kind of a mix of polar and nonpolar parts of a molecule. But for iodine, I2 being diatomic, it is purely nonpolar, so the only kind of forces would be London dispersion forces. So keep that in mind. You might see things that are sparingly soluble where we might think they should be completely insoluble, but because iodine is a large atom, and if you've got two iodines bonded together, you've got a lot of electrons. And if you've got a lot of electrons, then you're going to have stronger London dispersion forces, which makes it just slightly soluble or sparingly soluble in water. All right, let's get to some more questions here. So this one says, the survival of aquatic organisms depends on the small amount of oxygen that dissolves in water. The diagram above represent possible models to explain this phenomenon. Which diagram provides the better particle representation for the solubility of oxygen in water, and why? So, Andy, what is the polarity of the water? That's correct. It is polar. All right, and then Ian, what is the polarity of the O2? Also correct, it is nonpolar. And so for the polar-nonpolar combination, water being polar and oxygen being nonpolar, we wouldn't expect dipole-dipole forces, hydrogen bonding, but we should look for the possibility of London dispersion forces. So which of these two diagrams do you think better shows London dispersion forces versus dipole-dipole or hydrogen bonding or what have you, other intermolecular forces? Hopefully you chose C. In this, they're trying to show that the oxygen molecule has some London dispersion forces allowing the electrons to push slightly to the right, making it partially negative, and the other side partially positive, which would have a mild attraction to the water particles. And so that's something to keep in mind, that London dispersion forces, just like we talked about with the iodine on the previous slide, can cause some solubility even with nonpolar substances in polar solvents. All right, also keep in mind, thinking back to a couple lessons ago with Henry's law, the hotter the water, the less oxygen would be dissolved because there would be more rapid movement. And if there's more rapid movement, the chances of these molecules colliding at the right time with the electrons pushed to one side is more rare. All right, next question. A student is studying the properties of calcium sulfate and lead-2 sulfate. The student has samples of both compounds, which are white powders. The student tests the electrical conductivity of each solid and observes that neither solid conducts electricity. Describe the structures of the solids that account for their inability to conduct electricity. All right, so Amelia, what kind of compounds are calcium sulfate and lead-2 sulfate? Are they ionic, covalent? What type of materials are those? Good, they are ionic. If they are ionic, then obviously they're made of charged particles, and so it might be tempting to think that, well, if they're charged particles, shouldn't they conduct electricity? But they've discovered that neither of them do in solid state. So keep in mind, here's the answer, that ions, when they form those lattice structures that we've seen in a lot of different pictures so far this year, Those are attracted with the ionic charges pulling the positive cations to the negative anions, and they're fixed in that crystal lattice. And so when they're in that solid form, they can't move. There's no free charges able to move, so they can't conduct electricity. However, just keep in mind that if these ionic compounds are soluble, so remember your solubility rules, and if they're strongly soluble especially, they would be strong electrolytes when dissolved in water, which means they would conduct electricity, just not in solid form. So part B. The student places excess calcium sulfate in a beaker containing 100 milliliters of water and places excess lead-2 sulfate in another beaker containing 100 milliliters of water. The student stirs the contents of the beakers and then measures the electrical conductivity of the solution in each beaker. The student observes that the conductivity of the solution in the beaker contains the calcium sulfate and is higher than the conductivity of the solution in the beaker containing the lead-2 sulfate. Part B. Which compound is more soluble in water? The calcium sulfate or the lead-2 sulfate? Justify your answer based on the results of the conductivity test. So Heath, what do you think about this one? All right. Hopefully you came up with something along these lines. The calcium sulfate is going to be more conductive because it is more soluble. And so if it's giving more conductivity, there are more ions dissolved. So the way they've phrased it here, calcium sulfate is the answer. The greater electrical conductivity of the calcium sulfate solution relative to the lead-2 sulfate solution implies a higher concentration of ions, which comes from the dissolution or dissociation of calcium sulfate to a greater extent. So because it conducts electricity more, there must be more ions, therefore it must be more soluble. More of it must be splitting into ions. More of the lead-2 sulfate must be staying in that crystal lattice structure. All right? Remember, the more soluble ionic compounds are, the more ions they produce, and the more they conduct electricity, which is how we come to this conclusion. All right, the last part of this FRQ from a couple years ago, the left side of the diagram shows a particulate representation of the contents of the beaker that contains the calcium sulfate from that solution conductivity experiment. So you can see there's some crystal lattice at the bottom of the beaker, but there are some ions floating around which give it that conductivity. Part C says, draw a particulate representation of lead-2 sulfate and the ions dissolved in the solution in the beaker on the right in the diagram. Draw the particles to look like those shown in the right of the beaker. Draw an appropriate number of dissolved ions relative to the number of dissolved ions in the beaker on the left. So on your whiteboard, take a couple minutes and draw what you think the picture should look like for that lower conductivity lead-2 sulfate. All right, hopefully you've had a chance to scribble something down real quick. Ideally, you should have something that looks like this. There should be more crystal lattice at the bottom of the beaker because less of it is dissolving, and there should be fewer ions up in the water part. And they tell you to draw them as they're shown, so you should draw the positive lead like they showed you and the negative sulfate like they showed you. So this would be 1 point. You have to draw more crystal lattice at the bottom, fewer ions at the top to get that point. All right, hopefully that makes sense. And now let's switch gears to what I promised you for today, studying Beer's law. Now this is a process called spectrophotometry, and this picture is an example of one of many kinds of models of spectrophotometers. And in this kind of machine, we're going to put a sample of solution. It'll usually be some sort of aqueous mixture, and we're going to shine light through it, and we're going to see how much that mixture absorbs the light and how much of the light transmits through it. That's the basic principle. We're going to dig into the details quite a bit over the next several minutes. A couple things you need to remember, thinking back to earlier units in this year when we talked about photons and energy and frequency and wavelength. Those are still some equations that could pop up as part of an FRQ, you never know. And so in these spectrophotometers, we are only considering the visible light, which just has this limited range of wavelengths and frequencies. So you don't have to have those memorized, but you should know how to use those formulas that we learned earlier in the year. If they ask you about a wavelength or a frequency and give you the other one, you should be able to use that equation and be able to determine the answer. So that's just a quick reminder of some things we've learned before that are still connected and still could be asked about. Now, one of the things that's necessary for spectrophotometers to work is you need to have a solution that's got some color to it. And so as you can see at the very top of the screen here, if you're shining light that has red and green and blue in it, but the solution absorbs the red and the green, what would come through and what we would see is just the blue. And so that's basically what the spectrophotometer is reading, is what comes through and therefore contradicting that, what is absorbed. Many solutions have distinctive colors, and you need something with some color. A clear solution won't absorb any, or not any reasonable amount. And so we need colored solutions, but fortunately there are a lot of colors. Now the intensity of the color is usually an indication of how concentrated it is, which should make some logical sense. The more of it we dissolve, the darker it should be. And the less of it we dissolve, the lighter it should be in its color. And so that spectrophotometer is going to tell us what light transmits and also how much of it transmits. So here are some common ions, and you don't have to memorize this whole chart, but I've color-coded a few there that they often put on exams. So copper is often used as a blue color. So if they are talking about a blue solution, it's very likely it would have copper in it. If they're talking about a green solution, it's very likely it would have iron 2 or nickel 2 as the metal that's the ion in that solution. So for instance, the first blue one might be copper sulfate, and the iron one could be iron chloride, iron 2 chloride, or nickel 2 bromide, or something like that. So you're going to be looking for the colors that match. Now, Mn+7 is the ion that's in the permanganate ion, and so it's generally going to be some sort of permanganate, like potassium permanganate or calcium permanganate. And then the orange color is going to come out when you have dichromate. And dichromate is one that's going to be, again, bonded to some metal, probably potassium dichromate or sodium dichromate, something like that. So again, you don't have to know this whole list, but you should be somewhat familiar with those colors. And so maybe try to jot down a few of those colors. I'll give you a few seconds if you haven't started that yet. And if you have the ones that are color-coded there, you should be pretty good. And sometimes they won't even ask you to identify the color, but if you're somewhat familiar with it, then it might help you process certain questions. So I wouldn't spend a ton of mental energy to make sure you have these memorized. It's more important to have your ions memorized than this, but this is potentially helpful. All right, Beer's law. Now, how does this law work? Well, the law is actually an equation, and this at the bottom you can see is from the AP reference sheet. You can see the equation in the column that has the variables listed. You can see what each variable represents. All right, so Charlotte, would you read this slide for us, please? And as you can probably guess, we're going to break down each of these variables. We're going to discuss what they mean and how this equation can be used. So keep this tucked in the back of your mind for now. We're going to bring it back up in a few minutes. But keep this idea that the absorbance, which is the A, is directly proportional to the concentration. It's also directly proportional to the product of this epsilon, which is a molar absorptivity for the chemical you're studying at a particular wavelength of light, and then B, which is the path length, how wide of a space the light has to pass through. So here's a picture to help you kind of envision part of that. There are these little plastic rectangles, these rectangular prisms here, and you're going to have the chemical in it that you're testing. And it's clear plastic on two sides, and then there's kind of rough surface usually on the other two sides to grip it so it's not so slippery. And you want to put the clear sides facing the light. The light will pass through. The lighter the color, the more light passes through. The darker the color, the less light passes through. There is a point where you can make it so concentrated that the light can't pass through, and then the spectrophotometer wouldn't work. So the darker the solution, the more light the solution absorbs, and therefore the higher the concentration that solution has dissolved in it. Beer's law doesn't work for clear solutions like we mentioned because none of the light gets absorbed. And the greater the absorbance, the higher the concentration. Again, here's a couple more pictures, a different kind of spectrophotometer, the instrument we use. Sometimes they also might refer to it as a colorimeter. And if we have a chance after the exam, I do have one colorimeter so that I just own myself. And so we might use that and do a couple little tests once we get done prepping for the exam. If you look at the scale, the close-up here, you can see that there is not a linear relationship between the transmittance, which is on the top part of the scale, and the absorption, which is on the bottom part of the scale. And technically you can read either and use it, but since absorption is what's in Beer's law equation, the bottom scale is really what you're going to want to try to read. All right, now as we do the experiment, there's a few steps you need to take. First, obviously, you're going to need to make your solutions and put them in a cuvette and run the light through using the spectrophotometer. But there's a couple things we need to do to kind of set up the lab before any of that's going to really work. And so to do Beer's law, the first step is determining what is known as the wavelength of maximum absorbance. So to do this, you're going to read the highest point on the graph shown below. So you're going to take a graph, and on the spectrophotometer, there's usually a knob. This knob here is going to change the wavelength, and so you can graph what the absorbance is at a variety of different wavelengths. And you're looking for this peak right here to identify that maximum absorbance, or lambda max. And that's the one you're going to set it to. So you don't necessarily even have to graph it. If you just turn the knob on this dial and watch the absorbance and find the maximum, that's where you're going to leave it to do your test, where it has maximum absorption. However, if you graph it, you got better data, and graphs are something they often do test on the exam. So I wanted you to see that, and we'll have a question about that soon. So once you've figured out the maximum absorption, that's what you're going to rotate that knob to on the dial to make sure you have the correct wavelength that gives maximum absorption. All right, the second step is you're going to prepare a series of standard solutions with known concentrations of whatever you're testing, the copper sulfate, the iron chloride, whatever it happens to be. These solutions will help create a calibration curve for comparison. The standard solutions are typically made by diluting. So you'll usually get one solution of, let's say, copper sulfate, and then you'll dilute it to make it less concentrated, and then dilute that to make it less concentrated, and dilute that to make it less concentrated. And at each of those concentrations, you'll use the spectrophotometer to get a certain absorbance, and this will make your standardized curve. And so you can see here they've got 4 data points where they've measured the concentration, put it into the spectrophotometer, and read what the absorbance is. They've graphed concentration of the chemical that they chose to make in the lab using the dilution process on the x-axis, and then the absorbance that they get from the spectrophotometer on the y-axis. And this gives us a straight line. The third step then is to measure the absorbance of your unknown, which is really what we're trying to do with the spectrophotometer. Is we have a chemical, maybe we find one on the shelf that isn't labeled properly, we don't know the concentration. We can use a spectrophotometer, if we know what the chemical is, to use some of that chemical, of known concentration. So we make our own, make a standard, do the graph, and then we test this unknown and compare it to the graph. Now, ideally, you want the absorbance to fall in about the middle range of your graph to maintain accuracy. It definitely needs to fall somewhere in that range, because there are sometimes points where if it gets too concentrated, you don't get an absorbance. It blocks it all. So to determine the concentration, using the curve, you're going to find the concentration on the x-axis and the corresponding absorbance on the y-axis, and then you're going to see where they meet, and that would be the concentration. If you look at the absorbance on the y-axis and see where it meets the line, then go down and find the concentration. That would be how concentrated your unknown is. All right. So that's the basic principle. Let's look a little bit more at some of the detailed steps of doing the procedure, and then we'll practice quite a few problems. All right, so here's again a spectrophotometer. Here's another picture of a cuvette. You can maybe see on the screen a little bit of the texture on 2 of the sides. It's not perfectly clear here. And you want the clear side. There's a little diamond or triangle there on this to show that's the clear side that the light should pass through. You're going to place the sample in the cuvette, and you're going to put that into the spectrophotometer so that the light passes through it, and the spectrophotometer, the instrument's going to measure how much was absorbed. Now, a couple things. When you set up the cuvette, you do want to make sure it's clean and doesn't have any other chemicals from previous tests in it, but you also don't want there to be any water in it, because even if there's a few water droplets, that will change the concentration of the sample. This is a pretty small piece of equipment, so there's not a lot of volume in there, and just a few droplets can definitely change the concentration. So the way you can avoid that moisture, you could technically dry it out, but that's not super convenient. It's best just to wash it, clean it, rinse it with distilled water, and then put a little bit of the sample in it that you are going to test, shake it up, rinse it out really well with that, so that if there is anything left in the cuvette, if there are any droplets after that second rinse with the chemical, it is of the chemical you're testing. So that should hopefully remove all of the water, or at least the vast majority of the water droplets that might have been in there. So you want to clean it, rinse it with distilled water, and then rinse it with the sample you're testing before you actually do the test. The concentrations are key, so we need to know what they are. All right, this is a little more than you need to know, so I'm not going to spend a ton of time on it, but if you're really curious into the technology, the machine is going to measure the input or the intensity before and after the cuvette, and it's going to do some math with that. The math relationship is not something you have to know. This is not on the formula sheet, but just understanding it generally speaking might be a little bit of a blessing for you as you try to answer different questions. So by knowing what those two intensities are before and after, then you can find the transmission, and from the transmission or percent transmission, whichever one you calculate, you can then find the absorbance. So if you find the transmission just by taking the final intensity divided by the original intensity, then you would just take the negative log of that to figure out what the absorbance would be. Or if you find the percent intensity, then you would take 2 minus the negative log of that percent. Now again, this isn't something that you need to do mathematically, but just understanding that those two things do connect. The higher the transmission, the lower the absorbance, and vice versa. All right, so back to those graphs that we talked about. So this is a spectrum of some concentration of soda pop. Might be 7-Up, could be soda. Probably wouldn't be 7-Up because that doesn't have color to it, but maybe some cola or some root beer, something that's got a little bit of color to it. Orange Fanta. So this curve shows which wavelengths had a measurable absorbance, and we were looking for the peak, so we know how to set up our machine. And so if we look at this one, we can see the peak is right around that 475 mark, and so that's going to tell us what we want to set the wavelength to on the machine. So see if you're picking all these things up. A few practice problems here. So using this graph and using the wavelength at which most light is absorbed, lambda max, what is the lambda max for this compound? Go ahead and write that on your board. All right. The lambda max should be this highest peak, and it's pretty close to 450. So we should estimate 450 as the wavelength that we want to set the spectrophotometer to. Part B then. What color light would you use to analyze this compound? So looking at the lights that are down below, what colors of light should we be using? That is correct. Somewhere in that violet to blue range of light is right in the midst of this max. So our color of light that we should be passing through it will look violet or blue. Part C then, if that's what's being absorbed, what color does this solution appear to the observer as? Well, if we look at the graph, it's absorbing a lot of violet and blue. It's absorbing a fair amount of red too. The least absorbed is going to be the green and yellow, maybe a few hints of orange. So the color that you're going to see is going to be some combination of green, yellow, and maybe a slight bit of orange. But the violet and blue is going to be pretty much all removed, and a lot of the red is going to be removed as well. So it'll probably be some sort of greenish yellow color. So hopefully that makes sense in how you interpret this kind of a graph. Now let's get into more of the math. All right, so here we're looking back at a standardized graph, and let's see, who haven't I called on yet? I don't think I've called on Hannah. So Hannah, why don't you read this one for us? All right, thank you, Hannah. And on this equation is not on your formula sheet, but it is definitely one to help. You can tell it looks kind of like the gas laws that we looked with our 1s and 2s. So we've got our initial absorption divided by our secondary absorption equals our initial concentration over the second concentration. And so this equation I would put on your formula sheet. And I don't know that I would write both, because then you might just confuse yourself. Just pick one. If you like the A1 over A2 equals C1 over C2, pick that one and just write that one. If you prefer the A1 over C1 equals A2 over C2, which looks a little bit more like Charles' law or Gay-Lussac's law, where the A's and the C's are not together, then write that one down. Whichever one you're going to be able to remember the best. Don't bother writing both, because that, like I said, might confuse you more. But this one is one that will help you solve problems, and it's not on the formula sheet. It's just mathematically showing the direct proportionality between absorbance and concentration. All right, so that is one type of math you're going to have to think through. The relationship, if we have a first absorbance and then a second absorbance, and we know our first concentration, what is the second? And we could, as long as we have 3 pieces, we can always solve for the fourth. That is one type of question. Another type of question is thinking about the slope. So let's look at this part of the slide here. And let's see, Jocelyn, I don't think I've called on you yet either, so why don't you read this one for us? All right, thank you. You can see at the top of the screen, we've got the equation from the formula sheet. And you can see this is in kind of a y equals mx plus b format, because on the y-axis is absorbance, and y in the equation is absorbance. And then concentration is on the x-axis, so when we see concentration in the equation above, that c is the x value. Therefore, EB, E times B, or epsilon times B, is the slope. And so we've got y equals mx, where y is a, x is c, and the slope is EB, or epsilon b. All right, Max, why don't you read this one for us? All right, so this is probably outside of what most questions would ask on the AP exam, but if they happen to mention that the sample you're testing has a very high concentration, you should dilute it to make sure that light can pass through. Now, you should make sure you don't just randomly add water, but you should know exactly how much water and use the dilution equation, which we'll review in a few minutes here, to figure out, okay, if I know the dilution equation, I know that this concentration I'm putting into the spectrophotometer is a certain percentage. So maybe dilute it in half so that it's 50% of the actual concentration. And then when you find the concentration, you can double it to know the actual value. So probably beyond what they would ask. I haven't seen a question like that, but this does come from the chemistry with veneer information, and a lot of veneer materials get used on the AP exam. All right, here's another question. We're going to dig into this one. Use the plot to determine the concentration of a solution that has an absorbance of A equals 0.25. So figure out how you want to answer this question and then write it on the whiteboard. All right, if you have chosen the simplest way and just done graphical evaluation, that's probably the best route if it's an MCQ question. And you can just simply do the absorbance value over the line down to the concentration and estimate what that concentration is. However, if it is an FRQ, they might want more than just an estimation. And so with an MCQ, you can probably get close enough to highlight or identify the correct answer. If it's an FRQ and they're giving you this information, then they want you to use that information to actually calculate it. Now, you don't need to worry about the R squared value. That's just showing you the reliability of the data. But you do need to think through what the Y is on this graph, what the X is on this graph. You can see that the Y-intercept is virtually 0, so we can use 0. And you can also see what the slope is. And so again, what we looked at previously, thinking through this y equals mx plus b format, the y in this case is the A, the x is the concentration, the slope is the epsilon times the b from our A equals epsilon bc. And then if we just think about a plus 0 as your plus b there, that's kind of the connection and how you can visualize that relationship. And so if you're not answering a multiple choice question, have to calculate it, use this A equals EBC plus 0. We know what the slope is, 34.27. We know what the intercept is, 0.0032. So you can plug those in just to that equation. And then for any absorption, we can plug that in for A and calculate what the C is. And so since they said the absorption was 0.25, we plug that in for A, and we only have one variable left. And when we calculate that, we get 0.0072 molar. And you can see the unit on the x-axis is molarity, and so make sure you use that, either moles per liter or molar variable or unit there, sorry. All right. If you have questions, jot them down so you can ask me on Thursday when we're back together again. All right, example 2. Calculate the concentration of a solution, COCl2, so cobalt 2 chloride, that has the absorbance value of 0.400 at a lambda max. If 5.00 times 10 to the negative third moles per liter of solution of cobalt 2 chloride has an absorption of 0.175 under the same conditions. And I don't think I mentioned this earlier, but the absorption doesn't have a unit because it is a ratio of the transmissions. If you remember back to that relationship, the units are going to cancel when we find the transmission percent or the transmission value. Therefore, we're also going to be unitless when we find the absorption value. And so that is a unitless number. We have a few of those in chemistry. And so just keeping that in mind. Now, this is the relationship that I showed you before. You might have written down the other version of it, but it may help you to jot down what each variable is or make a little table to organize what you're given. So the unknown 1 has an absorbance of 0.400, and that's what we're trying to find the concentration for. The known is number 2, and I just chose 2. It doesn't really matter which one you pick. That is known as 0.175, and the concentration is 5 times 10 to the negative third, or 0.005 molar. And so we've got our A1 and A2, we've got our C1 and C2. I chose it this way. It doesn't really matter what you pick as 1s or 2s, but I chose it this way so that my unknown would be in the numerator, and I'll have a little less algebra to think through since I'm just solving for C1 versus C2 in the denominator. But it doesn't matter. As long as you do the algebra right, you can switch your A's and C's in terms of your 1s and 2s. So I plug the numbers in, I solve for C1, and the concentration, if the absorbance is 0.400, would be 0.0114 moles per liter. All right, so that is a second kind of problem. Again, if you have questions, jot them down in your notes. Bring them up when I'm back, hopefully on Thursday. I can't imagine I won't be. I'm starting to actually feel a little bit better tonight, but still have a fever. Definitely don't want to come give you this flu bug. All right, example 3. The molar absorptivity of ethanol in hexane at its lambda max is 15 liters per centimeters times moles. And so the centimeters and the moles are in the denominator, and the liters is in the numerator. Calculate the concentration of ethanol in a solution that has an absorbance of 0.652 with a path length of 1.2 centimeters. So this one is going to use the traditional absorbance spectrophotometry Beer's law equation. We are given the absorbance, so we know A. We are given the molar absorptivity, that number there with the crazy units. We are given the path length, which is the B. And so the only thing we don't know is what they've asked us for, the concentration. And if you look at these, since this is in centimeters and this is in centimeters, our units are okay. We don't need to change anything to meters. We could, but we don't need to. And when we divide all of this to the other side, the liters per mole is going to flip and become moles per liter. So our concentration will be in moles per liter, which is molarity. And so at this absorbance 0.652, the molarity of the concentration, or the concentration in molarity, is 0.036 moles per liter. Again, if you have questions about this one, jot them down. We'll talk about it the next time I'm back. All right. Errors in Beer's law. This is a pretty common FRQ kind of question. So if this is your standard curve and you're looking at numbers that are either above or below, they often will ask you, well, why would it be above or why would it be below? And so you really have to understand the basic premise of the procedure. So for instance, this dot that is above, it's possible that you got your fingerprints on the clear side of the cuvette, and those fingerprints have oil. And so that oil is going to absorb some of the light, which is going to throw off your absorption and transmission values. And so it's going to think it's absorbing more light than it actually is because your oils from your fingerprints are going to be absorbing some of that light. Or you might have had a dilution problem where you just didn't calculate it properly, or you didn't add enough water to get it right to the level in your volumetric flask, or your graduated cylinder, whatever you're using. So you might have it too concentrated, which would put its value too high. If it's below, then the cuvette wasn't water-free probably, meaning you either didn't dry it out or didn't rinse it with the chemical that you were testing. So that's why I'm saying water-free. It's rare that you would actually dry it literally, but you do want to get the water out of there by rinsing it with the chemical that you're testing. And so generally speaking, you would put a little bit in, swirl it around, dump it out, put a little in, swirl it around, dump it out. Maybe do that 2 or 3 times to make sure all the water is removed, and then pour your sample in and test it. So when you make the chemicals for your standard curve, you do want to make plenty, so you can do lots of rinsing and testing. And so these are a couple of things that might be reasons where your data point isn't on the standardized curve line. And again, something they often ask about. All right, now to finish up. In 2022, there was an FRQ, number 6 that year, that covered all of this. So on your whiteboards, I'm going to ask you to answer these questions as we go through. Some of them are pretty short to answer, but they're a lot to read. So let's go through this. It starts off saying a student wants to determine the concentration of permanganate in a solution. So it's probably potassium permanganate or lithium permanganate or something, but it's got permanganate ions in it because it's a soluble solution. The student plans to use a colorimetric analysis or spectrophotometry analysis because solutions containing permanganate have a purple color, like we learned earlier today. And then we see this graph of absorbance, and you probably already can imagine what one of the questions is going to be based on how we've practiced, and that is part A. To determine the optimum wavelength for an experiment that measures the concentration of permanganate, the student takes a sample of the solution and measures the amount of light absorbed by the sample over a range of wavelengths. The data are plotted in the graph shown. Identify the optimum wavelength that the student should use for the experimental procedure, or they might phrase it as what is the wavelength they should set on the spectrophotometer or the colorimeter. And write on your board what that number should be. You probably already have if you've been thinking about putting it on your board. All right, and it should be about 525. That's where the highest peak is. You don't have to average out any of the peaks. You're just literally looking for the highest one, and that is the one you're going to select as turning the dial to that wavelength on the spectrophotometer. Part B, still the same experiment. The student uses a stock solution of 2.40 times 10 to the negative third molar potassium permanganate to prepare the standard solutions of permanganate ions that are needed to construct the calibration curve or the standardized curve. And so they're taking something off the shelf in the lab that they know exactly what the concentration is. And now they're going to make that standardized curve from it. So here, part I of question B. The student uses a 100 milliliter graduated cylinder to measure a certain amount of potassium permanganate and stock solution, as shown, or a potassium permanganate stock solution, as shown in the diagram given. What volume should the student record? So thinking through what we've learned recently about a meniscus, what volume should you record? Jot that down on your whiteboard. All right, hopefully you've answered 92.0. We do need to show that since these are by ones, we should estimate to the tenths. And so we do need to show that tenths to get the accuracy value for this. This is one where significant figures of a measurement does matter. If you put 92, you will not get credit for that. So you have to recognize this has measurements to the ones, which means we need to estimate to the tenths. Some callback to early this year and Chem 1 stuff. All right, B part 2. Calculate the volume in milliliters of 2.40 times 10 to the negative third molar potassium permanganate that is required to produce 100 milliliters of a standard 1.6 times 10 to the negative third molar permanganate ion solution. So in other words, using this stock chemical you got off the shelf, how would you dilute it to make 100 milliliters that has this new concentration? And so we learned a couple lessons ago about the concentration equation, the dilution equation. So using this equation, see if you can calculate what that new volume should be, or how much that volume should be to create the proper concentration. All right, I know you might not have had enough time to get it all set up, but we are starting to run out of time. And so let me show you the work. We're using this M1 V1 equals M2 V2 calculation. Doesn't matter what you set as ones and twos, but I chose to make the M2 the 1.68 times 10 to the negative third molar permanganate, and it's going to be measured as 100 milliliters of that concentration. And then my M1, which is now in the denominator, is the given 2.40 times 10 to the negative third molar potassium permanganate we made it from. So how much of that original do I need to add and then dilute to 100 milliliters? Well, I would need to add 70 milliliters of the original and then dilute it up to 100 to get the concentration of 1.68 times 10 to the negative third molar. So that dilution equation we looked at before is an important one. And then let's wrap it up with this one. The student designs the following procedure to produce a calibration curve. Step 1. Prepare several standard solutions that have known permanganate concentrations by dilution of the stock solution. Step 2. Rinse the cuvette with distilled water. Step 3, rinse the cuvette with standard solution and fill the cuvette with the standard solution. Step 4, measure the absorbance of the standard solution with the colorimeter or spectrophotometer. Step 5, repeat steps 2 through 4 for each of the standard solutions. The data are plotted on the calibration curve shown. One of the data points indicated with an arrow on the calibration curve is below the line of best fit. So let's move on to the rest of the question. I've trimmed it down here on the screen, but I've got those steps still up here above. I still have the graph, and here's the question. Assuming that all laboratory equipment is functioning properly, identify which of the procedural steps the students could have executed incorrectly that would explain why the marked data point is below the line of best fit and justify. So give me a few seconds to read through those again and see if you can figure out which one would be the most likely step where the error occurred. All right, hopefully you've had a chance to think it through. The student probably made a mistake at step 3. If the cuvette was not rinsed with standard solution prior to being filled for the measurement of absorbance, the standard solution would be diluted because of the remaining water that was in there, and the absorbance would be lower than it should be. So that is a quick overview of Beer's Law, how it works, the math behind it, a bunch of examples, lots of practice problems. Hopefully that makes sense. We don't meet tomorrow because of the schedule change, so tomorrow is going to be an even numbered block day. So we'll see each other on Thursday. Hopefully I'll be back, and we'll do a couple quick reviews, see if you have any questions on this, and I'll ask you a few more review questions, then we're going to switch gears into the next unit on kinetics. So hope you have a great day, and I look forward to seeing you soon.